Yeah, my name is Pedro Morales, and I'm at UCSC currently. And today I want to show you a little activity that I did about randomness in Pi, and I've done it a few times already. And actually, I created this activity for Pi Day. This was before pandemic. I actually did it in the library in Austin. So I think Jennifer is somewhere around there. Hey, Jennifer. At this activity, I did it in the Austrian library, and I had a lot of kids attending this one, and they actually were very engaged and liked it a lot. And one of the key points in here is kind of like understanding, what does randomness mean? What does randomness mean? So let me just start by, first of all, checking if you guys are not falling asleep yet. Can you take maybe like some 20 seconds or something to write down in the chat, for you, what does it mean for something to be random? Would you guys mind just like sharing a few lines of, for you, what does it mean to be random? Because basically that's the core of what I want to present today. And let me just maybe pause my screen share so I can read your comments in the chat. Again, just in a few words, for you, what does it mean to be random? I like this idea of unpredictable, of no patterns, all over the place, no repeating. That's great. Defying prediction. I like that. I like that idea for sure. Let's see. Each possible outcome has an equal probability. That's very technical, Melissa. Thanks for that. Knowing some information doesn't give more information. Okay. So I think that we all have a notion of what randomness mean. Of course, we can go into the actual mathematical definition that we can think about in probability theory, but whenever we're working with people that have different backgrounds, this is a very interesting notion, because sometimes the most important thing that will arise is this thing about patterns, right? And I think that is very interesting to explore how patterns can relate to Pi, because a lot of us know Pi, have worked with Pi, maybe had nightmares about Pi when we were in school, and trying to find these things about randomness in Pi, I personally like it a lot. So the first thing that I like to talk about is, well, how can we relate randomness and Pi is through a circle. Usually this is a very common theme. Every time we have any Pi showing up in any formula is because there is a circle over there. So I like to kind of like underline that that thought. Whenever you see a Pi somewhere, it's because there is a circle. So that would be kind of like the main theme for the little thing that I have today. And usually what I try to do with this is, if it's in a room, if it's in person, is to physically have a circle drawn on tables, and to have like little circles or dots or pebbles or like Play-Doh little balls, and then people just throwing them at the table, kind of like to simulate a random process. But since we cannot do that right now, I'm going to show you actually a little script that I wrote in Python that will simulate that. So I know it's not going to be as exciting for you than throwing things at a table, but at least you probably will get a little bit of the feeling of what's the idea. So let me just tell you what's the process, what's the activity that will happen. Right now, it's going to be simulated with the computer, but if you do it with real life people, it's basically the same idea. You basically draw a square, and inside of that square, you inscribe a circle. And the idea is to throw at random some little balls or pebbles or dots, and then to count how many of those are inside of that circle. So that's basically the idea. It's just a counting thing. So I really like this because we really don't need to have a big background in order to count. So let me just share my Python script over here with you guys, because I want to show off that I can code in Python. Very simple things, but I can do. Okay, so hopefully you guys see it over here. And actually, I'm using Coco, which is a pretty nice notebook for Python. And you can actually do this in collaboration if you're doing it online. So that's one of the things that I like. So let me just explain a little bit while this thing is compiling over here. What's going on is, well, first of all, am I running this correctly? Let me just refresh just to make sure. What I'm doing is basically defining random coordinates for my points in a circle. And probably some of you guys know that this is basically a Monte Carlo simulation. And let's see if this guy actually wants to run, because if it doesn't want to run, then I'll have to try something else. Just give me 1 second. I don't know why I said acting out. I think it's shy because we have a lot of people. So, you know, sometimes programs are like that. All right, let me run it again and see if it works. And in the meantime, again, I was saying that I'm choosing X coordinates in my Cartesian graph at random between -1 and 1. And I'm choosing Y coordinates in my Cartesian coordinate at random between -1 and 1. And what I'm going to do is just to count how many of those, hopefully everyone can see my screen. I'm going to count how many of those are inside of my circle. Okay, so again, very simple counting thing. And the counting script is here what I have. So I did a total of 100 points. So I'm doing 100 points. And out of those 100 points, 71 were inside of that circle. So I'm just going to basically use kind of like solving for pi in the area formula for a circle. And that gives me a value of pi of 2.84. Okay. I mean, it's not great for sure, but it's not terrible either. It's close to 3. Okay. So what I'm going to do is I'm just going to increase. This is one of the great things about computers. I can just increase to 1,000 number of points. And out of those, let me count how many of those are inside of my circle. Okay, 792. And let's see how much better I got. Okay, 3.16. That definitely is much better. And this is one of the things that I like about doing it with a computer. Let's see if I can go all the way to 10,000. So over here, note that the formula that I'm using, kind of like for solving pi, the area equation, actually starts to make more sense. Because now you can see that basically I just colored everything, right? I kind of like colored everything. So now I can see, literally I can see with my eyes that I'm talking about areas. And really what I'm doing is comparing the area of a circle with the area of the square. And then the formula that I have down here makes a lot of sense. I'm basically just solving for that. And this is a little bit better, right? 3.11 and so on. Of course, this is not the best algorithm for computing pi. You will need to do a lot of simulations, and you probably can go all the way to maybe 1 million or 100 million in a good computer. And you will get some decent values for pi. But I think that this is a pretty interesting activity, okay? So let me show you a few more because I think I still have a few minutes to do it. One that I'm not going to simulate right now, it's Buffon's needle. Some of you guys probably know about this. I think you can still see my screen, right? Yes, perfect. So Buffon's needle, this is a similar situation. In this case, if you don't know the problem, basically the idea is that you grab a piece of paper and you draw some parallel lines with a certain distance between them. In order to make it easier, if you are going to use, usually you can use matches or toothpicks. So the distance between two parallel lines is actually the length of your toothpick or your match. The experiment is to put this piece of paper on the table or the ground and just to drop the match or the needle or the toothpick that you're using, and to repeat this process, okay? And then the two things that you will compare is how many times you're dropping this thing and how many of those times it's going to land touching one of the lines. So basically, it's another counting problem. And in this case, it's a little bit more interesting, that remark that I made at the beginning, because I said, every time that you are discovering pi in an equation, there is a circle involved. And this one is a little bit more tricky to find what is the circle that is involved. And usually, this is where you can promote a lot of discussion. You can ask people, where is the circle? Because we don't see any circles here. We just see a bunch of parallel lines. We're dropping something. We're not using any circles when we drop something. So the question is, where is the circle? And of course, I'm not going to tell you where is the circle because I don't want to ruin it for you, okay? But again, that's the most important question here. Where's the circle? And I have another one. I think I still have time, right? I still have a little time. So I want to share another activity that involves pi and randomness. And for that, let's see, can I check how much time do I still have left? Do we have time for?
Go ahead. We're good. Go ahead.
We're good? Okay,
Yeah.
Because I want you guys to not just look at me, but I want to give you something to do, okay? So let me tell you what's the idea in here. The idea in here is if you can either scan with your phone or with your device that QR, or if you can go to that URL, I'm going to paste it also in the chat so you can access it. Oops, I'm sorry. My bad. I took away the QR. Let me see if I can paste the URL in the chat as well. Okay. Let me go out of full screen. There you go. And I'm going to paste the URL in the chat so you can go over there. And you will see a form. You will see a Google form, and you can input two numbers. So please input two positive numbers, and try to make them between something like 1 and 1 million, just to help the computer not to die in the process. So please just choose two numbers between 1 and 1 million, two integer numbers between 2 and 1 million. And if you can, do multiple submissions. And maybe we can do that for 30 seconds or a minute or something like that. So again, the form will look like that, like this. And the idea is to input two numbers. And I have here basically just recording your numbers. You can see all the numbers coming up over here. And let me just get rid of, some people enter negative numbers. Only positive numbers. Let's do only positive numbers, okay? Let me just remove these ones over here because that is going to make my life miserable. So only positive numbers. And again, try to keep it between just 1 and 1 million to make things nicer. And here I have an approximation of pi based on the numbers that you are submitting right now. And if that doesn't amaze you, I don't know what I can say or do in order to show you that even pi can be obtained with random numbers.
But you're not telling us what the math is that correct?
And I can tell you the math. I can tell you the math in a second.
Oh,
so
okay.
The idea is that what I'm secretly doing is I'm checking if your numbers are co-prime. So the two integers that you're submitting, I'm checking whether or not those two numbers are relatively prime with each other. And then I'm doing a ratio as before. So I'm counting how many numbers have you submitted and how many of those are relatively prime. And again, we can go into more details, but basically there is an equation in order to get pi out of there. And you can probably see it here in my spreadsheet. And of course, I can go into the technical details, what is happening. but I have the same question as before. If somehow I'm trying to obtain pi out of this, that means that there is a circle. And this is a little bit more challenging. So again, I just want to leave because my time is up with that question. Where is the circle in relatively prime numbers? And that's what I have. So thanks for your attention.